Let's work on this one. Example 13.5. Estimate the area underneath the function square root 9 minus x squared using 4 rectangles and then 8 rectangles. So we're going to do 2 different Riemann approximations. Draw each Riemann sum as well, of course, because we're always going to draw the functions. We're always going to draw the sums. What does the graph of 9 minus x squared look like? Let's think about the domain there. 9 minus x squared has to be greater than or equal to 0, right? If I want the square root to give me a real number. So that means minus x squared is greater than or equal to minus 9. I multiply both sides by a negative number. It switches that inequality for me. I take the square root. X is only going to, or the function is only going to exist over the interval minus 3 to 3. Okay. So this function is only going to exist between minus 3 and 3. There's 0. And it's going to look like that. It's really the upper half of a circle, right? If you have y is equal to square root 9 minus x squared, you squared both sides, you get y is equal to 9 minus x squared. You rearrange that, you get y squared plus x squared is equal to 9. It's a circle centered at the origin with a radius of 3. And that's exactly what we have. But I only have the positive part because I took the positive square root. Okay, so that's the graph of the function. Now let's draw the Riemann sum. So I want to find the area underneath the function. So all the way from minus 3 to 3, first using 4 rectangles. So if I take that interval, minus 3 to 3, and stick 4 rectangles in. Oh, hold on. I'm going to leave that as in right now. So 3 minus a minus 3, 4 rectangles. 3 plus 3 gives me 6 over 4. That's 3 halves or 1.5. So each rectangle is going to be 1.5 units wide. So my first rectangle is going to go from 3 to 2 to 1.5. My next rectangle is going to go from 1.5 to 0. So this is, I'm a bad artist. This is not to scale. My next rectangle is going to go from 0 to 1.5. And then my last rectangle goes from 1.5 to 3, right? That's 4 rectangles. It doesn't say if I want to use a left hand or a right hand Riemann sum. Let's choose a left hand. So this first rectangle, I'm going to raise it up until I look at the function value at the left-hand point, but that's at 0. So that rectangle really has no height to it. I'm going to raise up this rectangle until the height is given to me by the function at the right-hand point. Sorry, left-hand point. Right? For this rectangle, I'm going to take its left and raise it up until I hit the function. I'm really not a good artist. And then finally, this last rectangle, its left-hand point on the function is my height. All right, so who's to say if this is going to be an over approximation or under approximation? I would have to say it's going to be an under because we're missing all of this area right there. But here's the picture. Let's estimate the area. So the area between minus 3 and 3 of the function 9 minus x squared is going to be approximately the sum of the areas of these rectangles. So my first rectangle, let's try to do this in colors. My first rectangle goes from minus 3 to 1.5, so it has a base of 1.5. In fact, they all do. In fact, because they all do, let's just factor out those bases and just add the heights of our rectangles. Actually, let me go slow now at this stage. My first rectangle has a base of 1.5. It has a height of 0. Right, the function value at minus 3 is 0. If you plug in minus 3 into this function, minus 3 squared gives you 9. 9 minus 9 is 0. Square root of 0 is 0. All right, let's change colors now. This next rectangle has a base of 1.5, and the height is given to me by my function value at 1.5. So if you plug in 1.5 here, what are we going to get? We're going to have to approximate. It's not a nice square root, but we get about 2.598. Right, so that right there is your function value at 1.5. All right, let's change colors because we're moving on to the next rectangle. This rectangle has an area of, its base is still 1.5. Its height is given to us by the function value at 0. If you plug in a 0 there, you get 0 squared is 0, 9 minus 0 is 9, square root 9 is 3. And hopefully, let's use yellow. No, it's purple. Our last rectangle has a base of 1.5 and a height given to me by the function value at the left-hand point, so 1.5. If you plug in 1.5 into this function, you get, again, approximation. It's an even function, so actually the same value as minus 1.5. You get 2.598. Okay, so what is the area approximately? We just need to add all these up. When you add all these up, you get about 12.294 square units. Okay, so let's see. N is equal to 4. So when we approximated the area with 4 rectangles, we get an area of about 294. Let's see what happens when we use 8 rectangles. So I'm just going to start from scratch. And we'll do the exact same thing, just now with more rectangles. So we're increasing the resolution on our picture. We should get a better approximation. All right, let's go back to that picture. It's the same function. So minus 3 to 3. It's that semicircle. There's 0. So how wide do I need to make each rectangle? B minus A over N. It's the same interval. It's 3 minus a minus 3 is a width of 6. This time I'm squeezing in 8 rectangles. 6 divided by 8. That gives me what? I can take a 2 away from everything. 3/4. So 0.75. So if I move over 0.75, my first rectangle is going to go from minus 3 to where? 2.25. 2.25. If I go from 2.25 and I move another rectangle over, oh, sorry, minus 2.25. All right, if I start at minus 2.25 and move another rectangle over, that puts me at minus 1.5. All right, minus 1.5 plus another rectangle puts us at, what is that? 0.75 minus 0.75. And then minus 0.75 plus a 0.75. That puts us at 0. And you can see it's going to be symmetric. So we're going to go, another rectangle is going to be 0.75. Another rectangle is going to be 1.5. And then minus, no, not minus, 2.25. And then finally over to 3. Right, 8 rectangles instead of 4. Let's do another left-hand Riemann sum. So let's get rid of the work that we've used now. All right, if we use a left-hand Riemann sum, this first rectangle is going to have trivial height because my function value, the height of the rectangle is my function value at -3. This next rectangle, I'm going to get my height from the left-hand point. This next rectangle, the height from the left-hand point. Same thing for this rectangle. In fact, same thing for all of these rectangles. So you can see at the middle there, where the function is not changing very drastically, the rectangles actually do a pretty good job of approximating. Cool. So let's shade in the areas that we're going to get. First rectangle has 0 area, that area, this area, and so on. Right, notice these rectangles don't extend all the way down to -infinity. They start on your x-axis, and their heights are given to you by the function value. Okay, so now we're approximating the area from -3 to 3 of the function f of x using 8 rectangles. So, oh, I forgot to do that on the very end. Okay, let's see if we can do think about this real quick. If it's going to be the first base times the first height plus the second base times the second height, so on and so forth. If all of these bases are the same, which they are, all of our rectangles have the same base, then you can pull that base out and just add the first height to the second height and all the way down the line. So let's do that. Let's pull out the base. 0.75 is how wide each rectangle is. So we can approximate this as 0.75 times the function value at -3, right? That's the height of my first rectangle right there, plus the height at -2.25 there, and we'll continue in this way. Oh, wait, do I have another one? No, my last rectangle is the height at 2.25, right? I don't have another rectangle using the height of 3. So that's it. And you can check yourself. Do you have 8 rectangles? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Okay, we can also use the fact that we know that this is an even function. If you go to your definition there and replaced x with -x, you would get the same thing. So let's clean this up just a little bit. F of -3 plus, and then the function at -2.25 is going to be the same thing as the function at +2.25, right? This point right here is the same height as that point right there. So I really have 2 of the functions at, I can just choose one, -2.25 or 2.25. For the same reason, the function value at -1.5 is the same value as the function at +1.5. This point right here is the same height as that point right there, even though it doesn't look it. I'm bad at art. The function at -0.75 should be the same thing as the function at 0.75. That height right there is the same value as that height right there. And again, if you don't want to use algebra tricks like these, you don't have to. But notice I took something where I had to evaluate my function at 8 different spots, and I pretty much cut it in half. But I still have f of 0. Okay. So, oops, not equal to, because we're making approximations. If you run through this, let me give the function values. All right, we've got 0.75 times the function at -3 is 0. We've got 2 times the function at 2.25, and that's about 1.984. We've got 2 of the functions at 1.5, that's about 2.598. We've got 2 of the functions at 0.75, that's 2.905. And then f of 0, that gives you a 3. Oh, again, not equal signs. So the area is approximately, when all the algebra clears the room, you're going to get about 17.974. So when we have 8 triangles, we get an area of about 17.974. All right, let's think about the second part. Knowing that this is the upper half of a circle with radius 3, how good is the estimate? Well, here we don't actually need calculus. We don't need to approximate the area using rectangles, because we know that the area of a circle is equal to pi r squared. So our actual area, no longer an approximation, this is exact, is pi times our radius was 3. So r squared was 9 pi. All right, if you plug 9 times pi into a calculator, you get about 28.274. So that's the actual area. So 28.274. Yeah, when we used more rectangles, it was a lot of a better of an approximation, right? This one way under approximated, and this one was still an under approximation, I reckon, because of that first rectangle. It doesn't pick up any of that area. But as you increase the number of rectangles, you get a better picture of the actual area.